Hello everyone, thank you very much for having me today. My name is Vlad, I am the CTO of QuestDB. Today we are going to talk about building efficient multi-threaded filters for SQL queries. I don't really like to talk about myself, but sometimes, like today, I have to. I'm a CTO by day and a hands-on software engineer by night. QuestDB used to be my side project, which I was building 5 years prior setting up this company. I'm also interested in building happy and productive development teams, as well as happy family, which is why I absolutely love playing with my kids. Every time I have a chance, silliest games because they're quite small. So, quick intro into who we are and what we do. You might be able to relate to a problem where it is much easier to generate a ton of data than to store it, let alone make it available for ad hoc analysis. We are working on solving problems of very fast data ingestion, the types that very often saturate incumbent databases. And at the same time, we solve problems of accessing the ingested data in near real time. Today, we're going to talk about the querying part. More specifically, we are going to touch on a subset of queries, full scan, where clause. This is a relatively small part of what we do, but it is quite interesting, quite nuanced, and relatively fresh in our minds. I'm sure you are well aware of SQL and the where clause. So where clause is often present in ad hoc SQL statements, and it is quite critical for us that all of these SQLs execute as fast as possible. A typical database would probably rely on indices, but in a columnar database, which is what QuestDB is, using indexes is not always the most efficient way to seek. This is because individual columns might be smaller in size than the index itself. For example, we use 64-bit value as a row ID, but we have data types of sizes 32-bit or less. In this case, index is not just taking additional space on disk, it also commands more disk I/O and requires more RAM. To emphasize the importance of a well-implemented full scan, let us take a look at the dark side of indexes. So ad hoc queries, handwritten queries, are likely to miss indexes altogether. Applications can sometimes deviate from indexes. So both deviated applications and ad hoc queries can be cushioned by fast full scan without QPS and latency impact. Absence of indexes also reduces storage requirements, and we all like that. Oh, and ingestion. Although we are focused on queries in this talk, I would not underestimate the impact of indexes on ingestion of machine-generated data. The fewer things we do during the ingestion, the better. And full scan and indexes can actually play along. We can index data ranges sparsely, which significantly reduces index size and leverages what we built for the full scan. At this point, I wanted to share a demo. So this is our demo website. So you can, it's totally open website, demo.questdb.io. You can do it at home, log in there, run queries you like. This is just example queries about filters. This is the base table. Sorry, it's a bit squashed. So this table has about 1.6-ish billion rows of data. And the following query kind of illustrates the filters that we built. So this is, we just scan this 1.6 billion rows of data for this predicate. The pickup latitude is 64-bit double value. And this is, we have execution speed at the bottom. I hope you can see this. It's 300 millis to do that. Another query uses more predicates combined or concatenated via end condition, and also this query include limit. So this is going to execute a filter and pick last 10 rows of the data. So 10 rows is useful because the data in the trips table is ordered by time. So this limit minus 10 returns you last occurring records, and this is execution time is just just below 200 millis, and this is again doing full scan on 1.6 billion row table, and a very similar query, except the limit here is positive and it takes first 100 rows of the same data. So, and this is about 85 millis to execute this data. This is again well, full scan, but I'll try and on the next slide, let's go back to slides, and I will try and explain how we thought about implementing this and how we implemented it. Okay, so this is slide. So for fast filter execution, we built a fairly generic scatter-gather code that would interface with user input in the form of an expression. This algorithm will scatter column fragments and gather these fragments back with row IDs in them. The scattered fragment is augmented by the user input, which is described by this method signature. So why do we have column fragments? We would like to partition data to increase liveliness of the concurrent scatter-gather logic. So let's take a look at how we integrate the filter function. So there are two ways to do it. So we can write an interpreter, which is quite straightforward and easy thing to do, or we can write a compiler, which is much harder, requires familiarity with compiler infrastructure and the hardware. But let's not forget that we want the fastest full scan, so we really have no choice but to go for the compiler. Writing compiler took us some time, which included choosing a compiler framework. So we considered LLVM, which is fairly good framework, but we thought it's too heavy for us. It produces large binary sizes, has fairly complex infrastructure. We wanted to keep the lightweight feel about QuestDB code base, so we went with awesome JIT, and no regrets here whatsoever. So the text parsing and AST, which is abstract syntax tree, are done in Java. The JIT compiler is in C. So to minimize the GNI call latency, we serialize AST to the non-heap intermediate representation, or IR, bytecode. This IR can be passed to the compiler in a single GNI call. Since we're going on a limb building the compiler, it would be rude not to take advantage of the array data layout in QuestDB. So we have compiler emit AVX2 instructions where possible. In some cases, compiler will also emit scalar instructions, but this happens only when we mix a particular data types in the same filter expression. And speaking of mixing, the compiler will also generate code that combines and or predicate results. After compilation, the scatter-gather code treats the filter function as opaque. These are responsibilities of the scatter-gather logic. You probably remember from the previous slide, the filter function the filter function arguments are column segments. So to prepare the correct input, the scatter logic uses the number of available CPU cores and the same metadata as the filter function. And there are two gather parts. The first gather part gathers the segments up concurrently and calls filter function via the GNI. This is a very coarse-grained call with a minimal latency impact. Although data originates from Java, the data essentially is C arrays. This would eliminate, well, this eliminates memcopy. Filter function gets to work on the contiguous memory addresses, with a tight loop inside filter function benefiting from CPU caches and prefetches. Then filter function produces row IDs and scatters column segments once again. The second gather part picks up both segments and row IDs to stream the data out. So let's zoom in on the scatter-gather concurrency a little bit more. So why do we need scatter-gather in the first place? Scanning column values should either, for performance reasons, saturate memory bandwidth if data is cached, or saturate sequential I/O of the storage device. To saturate either of those, the scan has to run multi-threaded. The scattered input is such that threads can begin work without fine-grained coordination. Although we don't want to make user wait for the entire scan to complete, we would rather begin streaming data as soon as the first data becomes available. So the scatter-gather logic works with our homegrown queue system. It's the system we use pretty much everywhere else in QuestDB. And this is a sneak peek at our queue and threading model. This diagram shows that our scatter-gather model goes beyond the scope of a filter execution. It also allows us to daisy chain other arbitrary parallel algorithms. So let us pretend here that the scattering thread in this diagram is doing an aggregation via the same scatter-gather algorithm. So the aggregation logic can scatter results gathered from the concurrent filter execution. This allows aggregation to commence as soon as filter produces first results. So worker threads are also quite generic. They're able to perform multiple jobs depending on which resources are available. Which brings us neatly to clarifying what those resources might be. For a worker thread, resources are always queues and sequences from which they consume work. Queues themselves are pretty boring. All I would say about them is they're circular and they store some data, really. All of the interaction with the sequences, with the queue, is done via sequences. Sequences will own a queue slot on request, so the data can be accessed without contention. The sequences never block. If there is nothing to own, a good example of this would be empty queue. They would signal to the worker thread there is nothing to do. A thread then can move on to another queue, sequence pair, and so on. And sometimes threads also publish to queues. But what happens when the queue is full? This is where our implementation becomes a little bit nuanced and, quite frankly, prone to race conditions which we had to weed out in tests. When publisher thread encounters full queue, it becomes a queue consumer. How to consume the queue and generally what to do with the full queue is in the description of the job worker thread is executing. This is what we refer to as work stealing. The publisher can unblock itself and perhaps other publishers, and therefore worker thread never really waits. But let us return to our filter subject and perhaps look at another force major event that worker threads can experience. And this event is, well, I call it enough, right? So what do I mean by enough? Several things, really. So enough time passed, aka query timeout. A network peer had disappeared and all the data we produced goes to the bin. So that's enough producing the data. It could be, the enough can be declarative, such as SQL limit clause that we shown in the demo. The circuit breaker is a work component that abstracts the semantics of the enough away from the algorithm. It helps us to keep filter implementation clean and uncluttered. Circuit breaker is evaluated at the beginning of each data segment to keep latency impact at the minimum. You saw circuit breaker in action on the limit queries, as I mentioned. It reduces execution time dramatically. I would not want you to go away thinking high-performance filter implementation ends here. There are plenty more tricks, which I will go over quickly, and if you're interested, I would be happy to elaborate on anything after the talk. I already alluded to fixed threads. Starting and stopping threads in Java is not fun, so we don't do it. We can also set thread affinity if we need to for fixed threads. Scatter-gather sequences are plentiful to avoid sequence contention when multiple SQLs are executed concurrently. Sharded queues take this sequence contention down a notch yet again. Bounded queues provide back pressure to trigger work stealing. And lastly, it is possible to construct a filter query that would return the entire data set. So to mitigate filling up entire RAM with row IDs arenas are emptied and refilled as rows of data being offloaded to either network or to another data processing algorithm. So what did we learn? So in this talk, we learned that full scans can be faster than you thought, hopefully. Full scans could be faster than index access in columnar databases. Fast full scan is not a standalone artifact. It can be reused as part of sparse or range indexes. There are a lot of nuances and potential pitfalls in the form of race conditions, and algorithms like this one have to be fuzz tested. It's not strictly econ, but this is something to take into account when trying to tackle a problem like this. So this is the end of my talk. I would encourage you to, as I mentioned, check the demo. It's publicly available. It's a freehand queries. You can run any queries you want to see what works, what doesn't, filters or other things. We have a fairly detailed write-up on the JIT itself and SIMD, how that's built. We also have comparison of this filter execution versus competition, so check it out. You can Google any title on the slide and you'll find it. So if you like this talk, please give us a star on GitHub. Thank you very much.